Okay, hi everybody. I'm Jay Falker. Thank you for the nice interview. I love Dr. J. The problem is I don't quite have the I can't dunk. I can't quite pull that off. So as introduced, I'm from Washington, D.C., and I'm a little bit intimidated. I'm going to follow Hakeem's advice, just be myself, because following these guys, so inspirational. I wanted to thank Karen for inviting me a chance to come down and be part of this. But I think I got more out of everything this morning than I'm going to give to any of you. So I'm really excited. Now, let me tell you about this kind of crazy title, right? Change the possible. Scientists, everybody should have a big problem. In fact, it's not even grammatically very good. But the challenge from Karen was to talk about revelation, trying to understand, change the universe. And the reason she thought the NIAC guy coming to talk might be good is we actually try to do these advanced concepts that on first blush people often would say are impossible. So it's right in theme. I resonated with stuff that the speakers have been talking about all morning. And I'm going to begin with this picture, which my colleague Jason, who helps me run NIAC, found, and he put in a presentation just last week when we were introducing our new research fellows to each other and to the program. And he was talking philosophy for a minute, and he was saying that ancient people looked up at the sky and they wondered. And he said that's pretty much what led to everything. And I agree with him because just looking at the picture, not the actual sky, fills me with wonder about those stars and worlds, and what we can learn about them, whether we'll go to them. And Jason talked about that leading to curiosity and discovery, and that leading to things like this. These are images from the original NIAC concepts, not my work, not even my direct program. It's the precursor that we just modeled, brought back, and expanded on a little bit. So they happen to be a handful of robotic concepts, and I actually asked a colleague, Kathy, to put together this graphic for a presentation over 3 years ago when we were just bringing NIAC back, and we wanted to be able to talk about what the original NIAC fellows had researched. Really briefly, this is a concept to send a few robots to go intercept an asteroid that might come too close to Earth, and a very clever way that they just nudge it a little bit, make sure that it misses. Down here, how many of y'all seen the Transformers movies? So this is not nearly as cool as that, but it's much more plausible. This was a reconfigurable robot, and a notion that instead of designing what we wanted and then launching it to go there and do exactly that, we could design something that could reconfigure itself autonomously without human involvement so that it could figure out what environment it was in and do a variety of science and engineering tasks and rearrange itself to do whatever's best next. This is called an entomopter, that sort of brownish bug thing up top. Has reciprocating wings, would flap like a dragonfly. And that was studied as a potentially much more efficient way to explore Mars than the wheeled rovers we have going around now or the airplane concepts that we have looked at. These beautiful bluish bird-like things are solid-state aircraft. You heard me right, I'll say that again. No moving parts, aircraft. They do flex, and in fact, this cylinder was their furled for launch configuration, so they could be sent somewhere if there's a moon with an atmosphere, then unfurl and glide, and possibly even actuate and slightly flap and extend their own range. And this beautiful constellation in the middle was actually the idea of our keynote speaker, Mason Peck, who was a NIAC fellow in the original NIAC before he went on to become NASA chief technologist. So everybody listen to me. It's worth paying attention to NIAC because look what you can rise to. This is, and Mason didn't know I had this, and this graphic was put together years before he agreed to go into this job. But it's the kind of thing we want people thinking about. This is a modular array, and it's held in place, the pieces, by flux-pinned interfaces. And that exploits a property of superconductivity and magnetic resistance. The big words don't matter. The point is, these things can be in position relative to each other and held in position without any energy required whatsoever or any active feedback. It sounds like magic. And that's exactly the kind of thing we want people exploring. So I'll step back and I'll give you an asset chart for just a second, and I'll talk about the context in which we brought NIAC back. Mason mentioned the Office of the Chief Technologist, and now I'm part of the Space Technology Mission Directorate, but we have 9 programs. And the point is just to say that they're all up there, and what we are trying to do is take things all the way from ideas to demonstration in space or whatever the relevant environment is. And we have ways to work with people all across NASA and universities and businesses and other agencies. And all the rest of this talk is going to be just about NIAC there in the middle, And yeah, we are kind of the center of everything, and I didn't even build this chart, but I was really happy to see that. So what is NIAC? NASA Innovative Advanced Concepts. This is a little research program, and we study innovative visionary concepts that we hope will change the possible in aerospace. Better way might be to show you some of the people involved, and this timing is terrible because we just met a bunch of the new fellows, and I didn't have time to update the slide and put in pictures of the 2013 NIAC fellows. But these were the Phase 1 and Phase 2 fellows last year, and you may know some of these outstanding individuals. But whether you know them or not, you know people like them. You may be people like them. Kathy Riley put together this chart with these words. I think she stole it from Apple, so whoever deserves attribution, cool. But boat rockers, rebels, innovators, fly-in-the-facers, out-of-the-box thinkers. That's the kind of people who make it in NIAC, because there's a lot of great ideas, and the semi-crazy ones that might just change the future, change the possible, are what this program is all about. So what do? 2 phases of study. The things we study are aerospace architecture, mission, or system concepts. So not focused technology, much more about how we use it. To be in scope for NIAC, it has to be exciting, unexplored, and credible. And I mean really exciting. We want to see a radical improvement, not just the next generation, or make possible something you cannot do today. Unexplored has to do with the scope of research. The original NIAC said it has to be new. Nobody has to have studied this before. That gets into some dicey stuff. What we really wanted to say was the stage of research at this point is just initial definition and feasibility and benefit analysis. What is it? How would you use it? Would it work at all? Does it deserve further investigation? That's often a paper study. Sometimes there's computer models or actual prototype and hardware demonstration, but usually it's analysis. And so if that's the right stage, you're in scope for NIAC study. The hard part is the credible. And the reason it's hard is we get hundreds of proposals every year in response to NIAC calls. That's wonderful. People have awesome ideas. But what we have to do then is get experts together. It's not me picking them or my boss. It's a peer review process. And we have to get people expert enough to know what they're talking about, but open-minded enough to consider things they may have never seen before, not the way we usually do it. And then they help us. They evaluate these things and say, yeah, these things have real scientific basis, and maybe a different way than we do it, but we think there's at least one plausible way it might work, and the benefit might be enormous. That's what NIAC is for. And we have a Phase 1 award that is $100,000, 9 months for that initial analysis. And Phase 1 is open to anyone in the US, NASA, outside, mixed teams, doesn't matter. Phase 2 is up to $500,000, 2 years for further development, and that's only open to people who have successfully completed Phase 1. But at any time in the past, including the original NIAC fellows. So you don't have to go directly from Phase 1 to Phase 2. So what are some of the things we're studying now? This is an eye chart. I'm not going to read them all to you, but I'll say that right now we've got 28 things that we're studying, and a better way was to try and talk about them in groups. The groups weren't important. They weren't designed before the fact, and then we selected things to meet them. But when I took a look at what we were funding, there's a bunch related to transportation, some related to human systems, some related to revolutionary construction or manufacturing, some related to sensing and imaging, some related to autonomous exploration. It can be literally anything relevant to aerospace goals, whether they're in our current plans or not. But this is too many words, so let's go back to some pictures. In the top left here, it's spider fab. This is an idea that says, instead of building structures on the ground and launching them into space, let's launch a canister of goo and some base materials and a little spider bot that can spin the structures, like a 3D printer, can extrude, and then can weave them into trusses, build the structures up there. And maybe with some other little spider bots, put some more advanced materials and electronics on there, and we can build a giant space telescope or a clever interferometer, and build a structure with much, much less mass than if we had to build something here on the ground, the way we built the Hubble Space Telescope or the segments of the space station. And maybe build structures that could only be built in orbit, completely different than anything that would ever survive launch. Potentially enormous mass savings and a potentially new way of designing. This is an image of the inside of a volcano, and it's done with muon tomography. Apparently, the scientists who use that have also tried to use it in Egypt to look for hidden underground pyramids and tombs and things. Now, what's kind of neat is nobody's tried to use it for space, but we have a couple NIAC fellows looking at it now to say, maybe we can get this to work with galactic cosmic rays and use it for the first time ever to see or understand the internal composition of the inside of an asteroid or a comet. And that's got scientific and exploration value. This, while sort of a station-looking thing in front of Mars, has the word stasis here, stasis habitat. Okay, stasis is science fiction. We can't just take people, magically put them in stasis, have them wake up at Mars or Jupiter or someplace. We would love to be able to do that. You wouldn't be bored on your trip. You wouldn't have to use things. What these guys have said is, okay, stasis is impossible, but hibernation is. Bears do it. Chipmunks do it. And we already cool people down into a hibernation-like state in medical emergency situations and then bring them back. So maybe we could do something like torpor, hibernation for people in the somewhat near and totally plausible future. If we could, and that's this NIAC study, then what does that do to your Mars architecture? Maybe you only need a little tiny transfer hub. And how much less air, food, water, everything do the people need? Now, they would need better autonomous systems around them. We still might not trust it. You might need one awake at all times. The guys are doing the trade study to actually analyze all that. But the cool thing, I can't wait to see the results so that we say, does this actually save a lot of mass and enable a Mars mission that's much sooner than we could do it? When you consider the psychological factors of not being bored and trying to stay healthy and a whole lot of other things, there may be a lot of reasons this is a positive approach. So it's worth studying now, and if it is, then we work with the medical doctors and everybody else and see how we can put it into exploration architectures going forward. On the bottom right is an image of a concept called contour crafting. The NIAC fellow who does this does it already on the ground just fine. He takes 3D printing of whole buildings, infrastructure. A little printer on a lightweight crane controlled by a computer can go and lay different designs, pretty complicated buildings. He contacted us because he said, maybe NASA could use something like this. And maybe the cement that I'm printing the buildings or floors or whatever with could be made out of the local regolith or the soil on Mars. In fact, the ISRU folks here at Kennedy, and there may be some in the audience, do a lot of things like this too and have worked with this team. This is kind of cool because they found in phase 1 that it does look like it can be made to work, and it might be even more beneficial on Mars someday. And if we could do this, you wouldn't have the cost and risk of sending humans. You can go and get some things ready with some robots first, and you don't have to bring any of that material to make it there. Last over here is kind of hard to see and a little bit hard to describe, and it's maybe the neatest aircraft concept I've ever seen. Picture the rotors of a helicopter, the things that whirl around. Now picture them spread apart from the center. So this yellow hub here, the rotors are now stretched out on tethers, real strong, lightweight cables. And why would you do that? Well, the rotors going around generate lift. That's good. But they also have mass, and they flex, and the downwash of each one interferes with the other. The farther you can make them from each other, the better for several reasons. So this concept is kind of brilliant because it only has a blade, the wing, that actually generates lift at the end. And it's separated far. You don't have to rotate as fast. And like the bullwhip example we had earlier, the tip is going really fast, right? The concept's name is eternal flight. Just a little bit of solar power on that central hub is going to keep this thing at about 80,000 feet indefinitely for free. And so we spend a lot of money putting up big geostationary satellites to be over the same spot on Earth. Now you can do this at 80,000 feet for a very low cost for all kinds of imaging, sensing, communication applications. One that's really cool that the proposers thought of is Wi-Fi everywhere. I mean, why not? Every town, every county, just stick up one of these birds someplace and make sure we've all got wireless internet access everywhere. So these are some of the kind of things that we look at. But NIAC gets an opportunity to reach even more visionary than that. This beautiful picture, it's done by an architect. I don't know how many have heard of an O'Neill colony, right out of science fiction again, 40 years ago. But Gerard O'Neill had this idea for a huge cylinder, not a space station, a thing you'd want to live in for generations. So it's big, it rotates for artificial gravity, and it's got a whole atmosphere biosphere in there. Wonderful, but we can't afford to do that. This is a concept for maybe a way we might get there in 10, 20, 30, 40 years. Anthony Longman is an architect who is teamed with tensegrity structure experts. Tensegrity structures may make this much, much less massive. We may be able to start with something small, only 2 launches maybe, with a way that it can be grown. And it might even be grown with material that we go get from the moon or other asteroids you don't have to lift out of Earth's gravity well. So there's a chance that, someday I can take a trip to this kind of thing, or my kids can. And that's what I at least like that people are trying. Or maybe it's crazy. Well, Arthur C. Clarke famously said there are 3 stages of reaction to revolutionary ideas. First, it's completely impossible. Second, it's possible, but it's not worth doing. Third, I said it was a good idea all along. I don't know how many of you have run into these, but I've run into them all the time. And our job here in NIAC is, okay, don't waste everybody's time and money on that one. But if it's not number 1, let's push as many as we can through 2 and 3, despite our own culture, despite the barriers, like everybody was telling you this morning. And on the way, it's not just about those visionary future things, and it's not just about NASA. There are benefits for people here on the ground and in the nearer term. These same things we're working on are helping with construction of buildings, medical rehabilitation, power generation and supply, navigation. So I invite you to look up at the night sky with me and wonder. And if you have any fantastic ideas, I want you to send them to us at NIAC. And together, we'll try to change the possible. Thank you.